So previously we have settled the question of the convergence of 1 plus 1 over 2 to the power of p plus 1 over 3 to the power of p and so on when p is restricted to real numbers. So it converges when p is greater than 1, but it diverges when p is less than or equal to 1. Now we are going to look at the power series expansion of the natural logarithm. So when we differentiate log of 1 plus x, we obtain 1 over 1 plus x, which can be expanded as this geometric series when x is less than 1 in absolute value. And we can now integrate this power series termwise to find that the log of 1 plus x is equal to this power series here, which is x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4 and so on, which is valid when x is greater than minus 1 but less than or equal to 1. So it does hold when x equals 1, which gives a nice series for log of 2, which is an alternating version of the harmonic series which diverges, although this is not the subject of the video. But when we replace x by minus x and we multiply both sides by negative 1, we find that a log of 1 over 1 minus x equals x plus x squared over 2 plus x cubed over 3 plus x to the power of 4 over 4 and so on. And now if we divide both sides by this series and we let x go to 1, we might, this question might be suggested to us of whether 1 plus a half plus a third and so on plus 1 over n and natural log of n are in any way comparable as n goes to infinity. So we suspect, for example, that their ratio equals 1 in the limit as n goes to infinity. And so we are going to investigate this. So we recall that the derivative of the natural logarithm ln of x is 1 over x. And so let us plot the graph of 1 over x. And now we see that these regions here that have been shaded, well, their sum to infinity converges. And the reason is that the sum of the first n triangles is an increasing sequence, and it is clearly bounded because you can slide each of these regions into the first rectangle and they will fit into this rectangle. So as it is a bounded increasing sequence, it means that it converges, so that the sum of these regions, these are not triangles, but they look like triangles. So the sum of these regions converge to some real number. And so why did I consider these regions? So these regions are the difference between the sum of the rectangles and the integral, that is the area under the curve. So for example, if I were to consider the first n rectangles, then the sum of the n regions would be the difference between 1 plus a half plus a third and so on plus 1 over n minus the integral from 1 to n plus 1 of 1 over x. And this integral is of course equal to the natural logarithm of n plus 1. So what we have done is, by considering the curve 1 over x, we have been able to compare this sum and this integral. And now what this means is that this sum here converges, and therefore 1 plus a half plus a third and so on plus 1 over n minus the natural logarithm of n converge. It converges as n goes to infinity because this limit converging is equivalent to this limit converging. So this limit exists, and we denote it by gamma. And we have, in fact, also established lower and upper bounds on gamma. So gamma is greater than 0, but is less than 1. And the reason is that the sum of the regions was definitely positive, but it was also less than 1 because you could slide all of the region into the first rectangle, which had area 1. So let me just go back to the curve here so that you see. So this rectangle here had area 1, so it's a square actually. And as you can slide the regions into it, so the sum of the regions is less than 1. So very well, we have established that this limit exists, and that and we have even obtained bounds on the limit. Now, so by the way, if you divide both sides by log n and then take the limit, it indeed shows that the ratio of this sum and the log of n equals 1 in the limit as n goes to infinity. So now that we have established bounds on gamma, we can try to improve our lower bound on gamma. And the way we do this is obvious. We consider the triangular portions of each of the shaded regions. And so it seems from the diagram that the hypotenuses of the triangles all lie above the curve. And this is indeed true, and we are going to prove this at the end of the video. For now, let us just assume this is true. So gamma is greater than the sum of these rectangles. And the sum of these rectangles is very easy to obtain. They all have a base equal to 1, and the heights are very easy to calculate. So the area is given by this sum, this infinite sum, which can be telescoped because this minus half cancels with this half, and this minus a third cancels with this third, and so on. And also the remainder term goes to 0 as we go further and further out into the series. So the sum of the triangles equals a half times the limit as n goes to infinity of 1 minus 1 over n plus 1. So that's a telescoping sum. So the sum of the triangles equals a half. And so gamma itself is greater than a half and is less than 1. So we have improved our lower bound for gamma. And now we have to justify the fact that the hypotenuses of the triangles, they were really above the curve. So the equation of the line segment from x equals n to x equals n plus 1 is very easy to calculate because we know the 2 points passing through the line. And if you check the calculations, you will see that this is the equation of the line segment. So what we have to show is equivalent to showing that when x is in the interval from n to n plus 1, then the curve, which is 1 over x, is less than the line segment, which is this equation. And we are going to prove this. So you are going to have to fill in the details because they are very easy to fill in, but the way to proceed is that we show that the inequality is equivalent to this quadratic inequality. But the quadratic polynomial has roots x equals n and x equals n plus 1, as you can easily solve and see. And as this is a parabola which curves upwards, so its vertex lies downwards, it means that it is 0 exactly when x is strictly between the two roots. So this implication is true. Therefore, the line segments, that is the hypotenuses of the triangles, they really lie above the curve, and this completes the proof of the improved lower bound for gamma.